computing in hopes that we can help CIOs better understand the complexities surrounding this issue. To do that, we put together a series of articles and real-world advice for you. ZDNet's Daphne LaPrance-Ronguet is here with me to give us a snapshot of this special feature. Daphne, let's start broadly. What is quantum computing?
That is a broad question. And to answer it, I'll start by sort of reminding you of what we're used to, which is classical computing. So classical computing refers to the form of computing that powers our laptops, our smartphones, all the way to the world's most powerful supercomputers. And as some of us may know, classical computers are powered by bits, which can take a form of 0 or 1 to sort of execute and order programs within a computer. So that's classical computing. Quantum computing, on the other hand, is a whole new way of sort of imagining computing. And to understand it, you sort of have to go to the field of science that it relies on, which is quantum mechanics. And that's what happens when you look at particles in their smallest states, known as their quantum state. And scientists for decades and actually for centuries really have noticed that when you look at particles in their smallest state, they adopt very particular properties that are completely different to the ones that we're used to in classical science. They're quite baffling. We don't really understand them, but they're very interesting. One of them, for example, is superposition. Quantum particles are capable of existing in a special quantum state, which is sort of existing in different states at the same time, as if they existed in different parallel universes at the same time. So even though we don't really understand quantum mechanics yet, computer engineers were wondering what would happen if we were able to take some of those quantum properties and apply them in the computer field. So, for example, we could use quantum particles to support data and to carry out calculations on a computer. So the idea of the quantum bit, the qubit, was born like this, and presumably with properties like superposition, we could use quantum bits to sort of explode the compute power available, carry out work with much more data, since we've got this sort of parallel universe thing going on, carry out multiple calculations at the same time in those different parallel universes. And so that's sort of the idea behind it, to sort of illustrate what might be quite abstract in more practical terms. For example, if you tasked a computer with the task of finding a needle in a haystack, what a classical computer would have to do is go through every single hay straw until it finds the needle, whereas a quantum computer would be able to sort of go through all of the hay straws at once until it found the needle. So obviously coming up with a solution to this particular problem much faster, much more efficiently. And obviously the more qubits you add, the more hay straws it can go through, so that the compute power also exponentially increases with the number of qubits. Now that's particularly interesting and important in the context of classical computing as it stands, which, as we all know, is sort of reaching its limits. You might be familiar with Moore's law, the law that states that we are increasingly packing a growing number of transistors on computer chips that are ever smaller, which means that eventually we will reach the physical limits of those chips. There will be too many transistors and the chips will be too small. Quantum computing, among many other things, offers a solution here, in the sense that it would allow for unprecedented exponential compute power to be unleashed, finding obviously a number of applications for science, but also for business.
Okay, I really like the hay straw illustration. That was a great way to help break down what quantum is. Next question, why is quantum computing important?
Why is quantum computing important is hard to tell at this point, because it is an emerging technology. It's still in its very early days, and actually what quantum researchers are doing really at the moment is trying to find out what those applications might be. For now, we're seeing a few sort of fields that might show promise for the day that we have a workable, fully fledged quantum computer. One of those is quantum simulation. So we could use quantum computers to better simulate complex molecules. So complex molecules have obviously lots of small interactions going on between the smaller particles that make up the molecule, which makes it very difficult for a classical computer to simulate a larger molecule. With a quantum computer, we would be able to simulate those larger molecules, which means that we could be able to design molecules with a specific purpose much faster. So that's got potential repercussions in drug design, but also in the design of new materials, for example, to create batteries that are more efficient. Quantum computing could also find applications in optimization. So researchers are working on optimization algorithms, going back to this sort of haze straw metaphor. If you need to find the most optimal solution between various different options, what a classical computer will have to do is try all those different possible options before deciding which one is the optimal one. The quantum computer would effectively be able to try all of those options at the same time, giving you an answer much faster. So for any company that's got to deal with logistics or supply chain management, that's obviously got huge business ramifications. It could solve the well-known traveling salesman problem. So when it comes to delivering goods, could establish the most optimal, efficient route, depending on different variables, time constraints, and other requirements. Again, it could hugely improve business outcomes when you take this on a large scale. Researchers are also looking at using quantum computers in AI and machine learning. Presumably quantum computers could work with a lot more data. It could sift through a lot more data, so we could improve the outcomes of artificial intelligence models. And we're also looking at using quantum computers in cryptography to develop new cryptography keys that would be even more reliable, even less prone to hacking, especially when you think about the fact that hackers are increasingly using larger amounts of compute power, which puts some of our cryptography keys at risk in the future. Quantum computers, once more, could have a role to play here in developing stronger, more secure cryptography keys.
So clearly the technology is important and highly anticipated. When can we expect to see quantum in the real world?
So that's the $1 million question. And again, the technology is so new, so early days that it's quite hard to tell. At the moment, quantum processors support usually less than 100 qubits. They rather support around 50, 60, 70 qubits. And most experts agree that in order to have a commercially relevant quantum computer, we'd need 1 million or more qubits. So obviously, the question is, how do we go from our current processors to 1 million qubits? You could say just add more qubits, obviously, but that's very difficult. Qubits are very fragile. They're very vulnerable to noise, to environmental interactions, which make them fall from this quantum state that is special and that enables quantum computing to have those special properties. So they require very careful manipulation and control. At the moment, for processors that have 50, 60 qubits, we're talking about rooms worth of equipment to manipulate and control qubits. So scaling that to 1 million qubit is simply impossible from an engineering perspective with current means. So that's obviously an area of focus for the companies working in the quantum field. And the companies working in the quantum field are increasing in number by the day, really. The tech giants like Google, IBM, Microsoft, Amazon are all investing in quantum computing. But we've also got a host of startups that are joining the quantum ecosystem. They're adopting various approaches. It's not a singular approach to quantum computing. You might have heard of superconducting. You might have heard of trapped ions, of photonics. All of those are different approaches that different companies are putting to the test. And obviously, all of them claiming that they will be the one to crack the quantum equation first. It remains to be seen which one will crack that equation. Researchers tend to say that we will not have a working quantum computer or useful quantum computer before 2030 at the very earliest. Some experts say it might take another 30 years. Some experts even say we might not be able to do it at all. It might just be impossible. And that this whole ecosystem really is just a hype that will die down as we realize that it's impossible to build a workable quantum computer. It definitely remains to be seen. There's a lot of money being poured into the field at the moment. The ecosystem is vibrant. What's certain is that if a workable quantum computer emerges one day, it could change the game across industries and bring about a new era for computing from a scientific perspective, but also from a business perspective.
All right, Daphne, thank you so much for this.